Okay, good morning, everyone. So it's 8 o'clock in the morning. Thank you for joining us this Friday morning in the Philippines, but it's Thursday night for those of you in the US. So this is the Philippine American Academy for Science and Engineers PAASE webinars. So Happy New Year. I believe this is the first event that we're hosting for this year. And to start us off, I'd like to call on the PAASE president, Mario Santo Domingo, to give us a few remarks.
Hello, everyone. Good morning in the Philippines and good evening for those who are here in the US and probably some of us who are in Canada. I'd like to, of course, greet you a very happy new year. As Dean Aviso mentioned, this is the first ever event for PAASE this year, and we're very glad that this is about climate change. Surely a very urgent topic, an issue that we need to face. When Dr. Raymond Tan informed me of his interest in starting the year off with this particular webinar, I was delighted and said, of course, we need to do this, and especially because of the COP26 that happened in December. So I'd like to thank, of course, Kay, Aviso, and our esteemed speakers tonight, Raymond Tan, Joey Comiso, and Just Santos. And it may be still too early, but there's a sequel to this. So next Friday, we'll have Dr. Leon Clark from the University of Maryland, who will give a talk on the social approaches to climate mitigation. Of course, I don't want to prolong this. I know you're all excited to listen to our speakers. So again, good morning and good evening to all.
Thank you very much for that, Mario. Okay, let me just start sharing my screen. Hold on. Okay. So, good morning, everyone. So we have with us very esteemed speakers, some of the top climate scientists in our organization, and maybe even in the rest of the world. We have Joey Comiso, who received his bachelor's degree in physics from the University of the Philippines, Diliman, and his PhD also in physics from the University of California at Los Angeles. He did his postdoctoral work at the University of Virginia and did research in nuclear and particle physics at the Lawrence Berkeley Laboratory, Los Alamos National Laboratory, and the NASA Synchrocyclotron Facility before joining the NASA Goddard Space Flight Center to do research on climate change. So he spent a lot of years together with NASA, and we'll learn more about his work in NASA later today. Then we have Just Santos, who is an associate professor from the Department of Engineering Management and Systems Engineering at the George Washington University. His research interests lie at the intersection of systems engineering, disaster risk analysis, and economics. Professor Santos is one of the principal investigators in the 2018 Mitigation Saves report that has been cited by the US Congress and President Biden, as well as many journals, news media, and research agencies across the world. So he is known for one of the key developers of the inoperability input-output model, which utilizes and transforms economic input-output accounts for disaster risk analysis and applications. Finally, we have Professor Raymond Tan, who is the current Vice Chancellor for Research and Innovation of De La Salle University. He is also a distinguished full professor of the Department of Chemical Engineering and a university fellow. He is also an academician of the Philippine National Academy of Science and Technology. His work is on systems engineering with applications to carbon management and process integration, and is the co-developer of the carbon emissions pinch analysis algorithm. He was actually included in the Reuters hot list of the world's top 1,000 climate researchers. So without further ado, I'd like to welcome our speakers for tonight. I think we'll have Joey first.
Can you see me?
Yes, we can see it.
Okay. Okay, greetings, everybody, and Happy New Year as well. First of all, I would like to thank Raymond and Kay for inviting me to this PAASE webinar on climate change. So I'll talk about the anthropogenic climate change and its potential impact. As Kay said, I work at the NASA Goddard Space Flight Center. And just to give you an idea how the facility looks like, the one on the left is the main gate for Goddard. This is where we store satellite data. My God. And this is our building, the Earth Sciences building. This is for scientists who use a satellite to look down on Earth and study the Earth system. And this is the space science building where scientists look at the sky and study the universe. So the key problem have been anthropogenic climate change, and I was lucky to be invited to be a coordinating lead author of the IPCC 2014. And I took a little bit about that. Observationally, we look at the trends in surface temperature, solar activity, volcanic activity, and internal oscillatory variability, as well as the anthropogenic component. And the plots from 1880 are shown on the right. You can see that the solar component doesn't have a trend. The volcanic component had two main events, including Mount Pinatubo eruption, which you see in the shaded area to the right. But the internal variability component also doesn't have a trend. And the only one that seems to mimic what we see in the temperature is the anthropogenic component. So that gives you an idea about the correlation of the anthropogenic component with the temperature. Another thing that's overlooked is the one on the left, the fact that the atmospheric component of carbon, the trend seems to be similar to that of the PCO2 as observed in the ocean. And the rise in PCO2 is inversely proportional to the pH of the ocean. So that means that the ocean has been getting more and more acidic. And this acidity has been observed in many parts of the Earth. If it continues on, then we may have a large part of the ocean to be corrupted and basically useless. What you see here is basically the source of emission. Contributions from Europe and US used to be the highest, but the one for the US is almost constant now. And the ones from Europe has come down. But if you look at China, it was number 3 in 1990. It overpassed Europe in 200 and the US in 2000, 2004. And now it's more than twice that of the US. So to solve the emission problem, I think we have to get all the countries of the world to be involved. And you can see that India, which has almost the same population of China, is also industrializing very rapidly. So that will be a big problem as well. Raymond asked me to look at the risk, and I would like to mention a few of those risks. One of which is one I've been reporting about myself since I was sitting and developing data that's associated with it. I I was a member of the cryosphere branch, and we studied the Arctic region, mainly because it's supposed to be the area where you find the early signals of climate change. So I'll go over this quickly since I'm only allowed 8 minutes. The Arctic perennial ice have gone down from about 8 million square kilometers to less than 4 million square kilometers over a period of less than 40 years. And that means that if this continues, then the ice cover in the Arctic basin will basically be a blue ocean. And that means that much of the solar heat that's absorbed in the Arctic basin will be absorbed since the albedo of ice is high compared to the liquid ocean, and the liquid ocean would then absorb most of the rays from the sun. That will cause a general warming in the Arctic region as well. So another observation that we have made is the fact that the Greenland ice sheet, it is high in elevation, so it's normally cold on the top. But in recent years, what you see in orange here is the area where it melts. And there have been episodes when the melting was almost over the entire area of Greenland. And the reason why this is of great concern is the fact that what you see in the left is when it melts, much of the water goes down, and it goes down all the way to the bottom, where it can serve as a lubricant that makes the ice more dynamic and it becomes vulnerable. We also see similar signals in the Antarctic. You can see in red the areas that are vulnerable, and especially the West Antarctic. So the two areas, West Antarctic and Greenland, is 7 meters sea level rise for Greenland and 6 for West Antarctica. You can have a sea level rise of as much as 13 meters. So this is how the sea levels have been going up in recent years. And you can see that West Pacific area is very vulnerable, and that's close to Manila. And if you look at the plots over here, there are actually areas where it doesn't change much, like San Francisco. It actually goes down in Stockholm, but in Manila, the increase is 3 times that of global average. So we have had the strongest typhoon in the Philippines. Haiyan was stronger than any other typhoon recorded by satellites. A lot of damage and a lot of people died. And we actually studied this and come up with an idea that before Haiyan, the Pacific Ocean was actually the warmest ever recorded by satellite. So we had Typhoon Ondoy, which is also unusual. It affected a lot of people. We have lots of fires around the world. And what you see on the right is the trend. So there's a trend for more and more extensive fire. And as a member of the IPCC report, we actually look at representative concentration pathways, which means what happens if you have different levels of atmospheric concentration. If we keep the concentration constant at 421, then we get what we see here in blue, and the temperature stabilizes right away, and we can save the Arctic ice pack. Then if we leave the atmospheric concentration to to go as fast as it has been, then what you see is the one in red, and you can get the temperature to go up to as much as 3 to 6 degrees centigrade. So the IPCC 21 just came out, and they were using CMIP6, which is a more advanced version of CMIP5. And they included an issue, a condition where the percentage atmospheric concentration is at a level where the percentage is allowed to decrease and up to 0. And that's what you see here. These are different components of the greenhouse gases. This is for carbon dioxide. These are non-carbon dioxide greenhouse gases, and this is for aerosol. So for SSP1, 1.9, we can go up to as much as 1.5 plus or minus 0.3. And this is a contribution from carbon dioxide. So it's the most potent greenhouse gas in the atmosphere. This from the other ones. And then for aerosol, it's actually negative because negative aerosols provide a negative impact on the temperature. So these are the other scenarios. For 2.6, as I provided earlier with the IPCC 2014 prediction, and it can go up to 1.8. For 4.5 can go up to 2.7 with SSP3 7.0, it goes up to 3.5. And then this is the business as usual, where it goes up to 4.5 or higher. Wow. I don't know what happened. So actually, I don't see the stuff. This is COP21, COP26 compared to COP21. Actually, these are the requirements for COP26 that we have had, that they agreed on in Scotland recently. The key with this convention is to limit the increase in temperature to 1.5. We already know that an increase of 1 is already causing all the problems we've been observing. So what they want is not to increase the temperature any higher than 1.5 from what we had during the Industrial Revolution. So there's a call for coal to be phased down. Actually, they wanted it to be phased out, but China and India objected to the language. 120 countries pledged to halt deforestation. 100 countries pledged to halt emission of methane by 2030. More than 100 countries pledged to end the sale of cars with internal combustion engine by 2035. And they want increased support for developing countries who suffer more from greenhouse gas warming. And then there'll be another meeting next year in Egypt, and they call for all the 197 participating countries to report the progress of their commitment. So That's basically the end of my talk.
Thank you so much, Joey. Now we move on to Just.
I'll first share my PowerPoint. All right. Okay, can you confirm if my PowerPoint shows?
I can see it from my end, yes.
Okay. So good morning to the Philippines and good evening to the participants located in the United States. So I'm Ju Santos from the George Washington University. I actually just came from teaching, and it's such an honor and privilege to be in the same webinar with my esteemed colleagues, Doctors Joey Comiso and Raymond Tan, on the important and urgent topic of climate change. So, quoting from IPCC, Intergovernmental Panel on Climate Change, which Joey also alluded in his talk. So this is from the 2021 recently released assessment report. It says here that human-induced climate change is already affecting many weather and climate extremes in every region across the globe. And evidence of observed changes in extremes such as heat waves, heavy precipitation, droughts, and tropical cyclones. I am sure that almost everyone here has heard of IPCC, and it won the Nobel Peace Prize in 2007. So climate change consequences can be decomposed into two categories. The first one is the so-called stock losses. So these are the damages and direct disruptions to physical and human capitals. The second category is flow losses, also called by economists as business interruption or BI losses, causing the loss of productions and or consumptions. Notably, the focus of my talk, this is gonna be a really short talk, will be on the business interruption losses. So whenever you see BI, the acronym BI, it stands for business interruption, which account for a significant percentage of the overall economic losses pursuant to disasters, as what many research scholars and insurance agencies have emphasized. You can see at the bottom of this slide, it underscores the fact that for 7 years in a row now, that business interruption still ranks as one of the top contributors to the economic losses due to climate change. Moving on, so this slide is just meant to showcase some of the models that I'm currently using and I've also used in the past with students such as Krista Yu, who's a faculty also from the De La Salle University, and Joanna Resurrection from the University of the Philippines. So examples of the models and data sets showcased in this slide include the input-output model, computable general equilibrium, and recently I've used the in-plan data, which is a more sophisticated version of input-output tables. So here is an example of a low-resolution input-output table. It's still real world because it's based on a 15-sector aggregation scheme of the Bureau of Economic Analysis. You would expect that the bigger tables would comprise of nearly 500 sectors. So if you can see my cursor, I'd like to point your attention to the number 2.48. This is what you call the output multiplier. So the output multiplier means that if there's a $1 demand increase for the manufacturing sector, so the highlighted sector in red is the manufacturing sector, it means that the total output resulting from that $1 increase in demand would be 2.48. So if we try to decompose 2.48, subtract $1 from that, we'll be left with 1.48, which is the so-called indirect effect. As you can see in this real world example, the indirect effect caused by a stimulus in demand is actually much more than the initial stimulus itself. Same can be said with the yellow highlighted cell here, which is 2.25. That's the output multiplier for the agriculture sector. In almost all countries that I've looked at, manufacturing tends to be the one that gives the so-called biggest bang for the buck. So whenever we start at at the beginning of the month, we look for jobs report, and you would see that a particular focus is made for manufacturing jobs because it's the one, as what I said, that gives the biggest bang for the buck. So you might think that the numbers here, 2.48 and 2.25, and the other numbers you can see at the bottom are just a few dollars and a few cents. But when contextualized with respect to the GDP of a country such as the United States, still considered to be the richest country in terms of GDP at $21 trillion. So if Kay has $21 trillion, I'll probably make her my best friend right now. So this is just an example of an input-output table. There are lots of input-output tables available not just for the United States, but for regions within the United States and also for other countries like Philippines. So this is just a snapshot of the mitigation saves study, which calculated the BCR, or the benefit to cost ratio for disaster mitigation investments for different disasters, including riverine flood, hurricane, wind, earthquake, and wildfire. We took the average, and on average, it used to be 4:1 benefit to cost ratio, but in our most recent computation, it's now been upgraded to 6:1 ratio. So this 6:1 ratio is a convincing or compelling ratio that can be used to justify the investments for mitigations, disaster risk management solutions in order to make our nation and our infrastructure more resilient and more adaptive to the impacts of climate change. So just a few months ago, I was also involved in a project that studied the effect of liquefaction on Portland Airport. So here you can see Portland Airport with one of its runways. So what would happen when there's a severe liquefaction that would affect this runway? It would cause structural integrity issues with the runway, maybe causing some sinkholes, causing inoperability to the runway. And if we look at the business interruption losses, there will be lots of economic damages due to this being airport, one of the most major airports in the northwest region of the United States. So the team determined that mitigating the PDX, or Portland Airport runway, would result in a much higher BCR, which in this case is a 12:1 ratio. This reminds us of the old adage popularized by Benjamin Franklin: an ounce of prevention is worth more than a pound of cure. So in this computation, it's really a sophisticated computation involving geotechnical engineers, economists. And we also took into consideration, when computing the benefit to cost ratio, the time value of money, as you can see here with the growth rates and the discount rates showcased in this table here. So in conclusion, climate change has increased the frequency and intensity of disasters. It has been found that 70% of the losses can be attributed to business interruption losses. This is a concrete evidence that climate change management should not only focus on individual infrastructure systems and economic sectors, but rather holistically and in an interdependent manner to nip in the bud the costly ripple effects of business interruption losses. And with that, I turn the floor over to our fantastic, phenomenal MC Dr. Aviso, Dean Aviso rather.
Thank you very much, Just. I thought you were going to turn it over already to Raymond.
No.
So, okay, now I'm turning the floor over to the next speaker, Raymond Tan.
Right. Thanks very much. Good morning. Good evening, everyone. I'll present what I consider to be a very strong case for negative emissions. And I'll begin by quoting this 45-year-old paper by Freeman Dyson. Long before climate change was a topic of public discourse, back when it was a distant threat over the horizon, he wrote a very visionary paper about a climate emergency in the future and some of the ways by which we can rapidly take out some of the excess carbon dioxide and, of course, also figure out what are the potential pitfalls of doing so. And it's strange because I read this paper 5 years ago, back when it was 4 decades old, and here we are facing the very climate emergency that he envisioned. About 4 years ago, the IPCC released a roadmap for keeping warming by the end of the century to well below 2 degrees Celsius, and actually as close as we can get to 1.5 degrees Celsius. The reason for that is every fraction of a degree counts.
I think we lost you, Raymond. Okay. So I think we lost Raymond for a while. So let's just wait for a few minutes for him to connect. Yeah, so I hope that everyone, you can start thinking about your questions for our discussion later. All right, I think we have Raymond back.
I'm back. That was a very well-timed business interruption. It's interesting that it happened just as I was beginning, but I think this is where I left off.
Yes.
Now, the challenge on a planetary scale is to keep global warming by the end of the century to as close as we can get to 1.5 degrees Celsius, because every fraction of a degree counts in terms of the local impacts that Joey spoke of earlier, sea level rise, extreme weather events, and such. Now, what's needed, because this is being driven by the accumulation of greenhouse gases, and particularly carbon dioxide in the atmosphere, it's estimated that what we need to do is to take that historical trend of climbing greenhouse gas emissions that goes back literally thousands of years in human history, and to halt it, and then in the span of one human generation, by about the middle of the century, to reverse that and bring it down to net zero, down to about mid-century, which is one human generation from now. How do we achieve this? At around the turn of the century, the concept of stabilization wedges was proposed. The basic idea is you don't wish for a single silver bullet to solve the problem, but you take the available technologies and you stack them up like pancakes, and you get cumulative reductions in greenhouse gas emissions if you deploy them to the maximum extent. What my main point this morning is that because we're trying to get to net zero on a planetary scale, at some point, there will have to be what are known as negative emissions technologies contributing to the stack of pancakes that I spoke of. And very quickly, I think it's very instructive to go back to the basic carbon cycle. So this is an IPCC cartoon which illustrates the major carbon flows. The mental picture that you get out of this is simply that the main problem is not so much carbon. The amount of carbon on the planet is fixed. What we're doing as a civilization is transferring that carbon from compartments like fossil fuel reserves and vegetation, and putting too much of it too rapidly into the atmosphere via these what are known as positive emissions. So the concept of negative emissions is to engineer ways by which we can do the reverse and apply techniques that take carbon out of the atmosphere and put it in other compartments. So for example, some of the techniques would be to increase carbon stock in biomass, whether that's in vegetation or soil biomass, whether it's live or dead biomass, but that can be a huge carbon stock. There are geological reservoirs, for example, where we would find natural gas. Once these are depleted, these are essentially containers in which you can put carbon dioxide if you can find a way to physically or chemically remove it from the atmosphere. We could take naturally occurring weathering processes. These are when minerals or rocks react with water and carbon dioxide and traps that in the form of carbonates or bicarbonates, thus taking it out of the atmosphere. That is a geologically slow process. So you could engineer that so it becomes fast enough to be meaningful over a multi-decade time scale that we need. And there could be an artificial increase in ocean carbon uptake, for example, through alkalinization or through fertilization. Of course, that is going to have to be done, taking into account potential risks to marine life. But essentially, these are techniques that can conceivably work and can be engineered to the scale needed. Now, is that all science fiction? As a matter of fact, no. There are companies now which have started to commercialize. For instance, here's a picture of a direct air capture plant in Iceland. And what this does is it skims from the atmosphere, from the 400 plus parts per million carbon dioxide into the atmosphere. And it takes out, through a physical chemical process, takes out the carbon dioxide. And then you simply find a geological reservoir to dump this captured CO2 in. And eventually there are people who believe this can be scaled up to the point where we're taking out multiple gigatons of carbon per year throughout the planet. This is still in the early stages, so it remains to be seen whether this will be the winning technology in the future. What we do know is because we have the technology available, there are startups that are trying to push commercialization, that there will be a carbon drawdown economy in the future. In the Glasgow Agreement, there's a passage about carbon financing, and of course the financing will certainly be the driving force, but eventually there will need to be firms that actually take these technologies and scale them up. And companies that are trying to cut their emissions would either do it in-house, but what's more likely is for many of these, like airlines who would have a hard time decarbonizing, would probably buy carbon credits from other firms. And some of these firms in the near future would just, their business models would be built around creating and selling negative emissions credits. So that is something that's happening in the future. My own contribution to carbon management goes back about nearly a couple of decades. And I've worked on developing algorithms to help plan and optimize decarbonization portfolios, whether at the scale of entire countries or cities or even individual corporations. And in 2020, and then again in 2021, I wrote a couple of brief perspective papers on negative emissions. What are the threats and barriers, and what are the opportunities? Very quickly, the main barrier, which actually Freeman Dyson also mentioned, is that there will be physical constraints on how much negative emissions you can generate. Even if you speak of the most obvious solution, which is reforestation, that is not going to come without a price. You're going to need land, large amounts of water resources, nutrients as well, fertilizers and such. So there needs to be an optimization approach here, because you don't have unlimited land, unlimited water resources when you start decarbonizing on a massive scale. Now, much more recently, in terms of opportunities, there is going to be a carbon drawdown economy that can piggyback on, for example, circular economy legislation that exists in China, in Europe, where you can take, for instance, industrial waste and use that for enhanced weathering, so that you solve two problems at once. But just so we can proceed with the discussion, these are what I think are the research needs when it comes to negative emissions technologies. First of all, given the scale of greenhouse gas emissions, which is roughly about 40 gigatons per year of greenhouse gases globally, anything less than gigaton level is just would be a drop in the bucket and would be insignificant. So when we speak of scalability, we need to look at 10 raised to 9 tons per year for it to be worth discussing. And because of that scale, we need to understand what happens when we take negative emissions techniques or technologies and we plug them into background systems. And just as a thought experiment, if you were to try to do what Dyson proposed 45 years ago and do massive scale reforestation, afforestation, that sounds like a good thing, but that is going to have other environmental consequences, which you would need a systems thinking approach to be able to anticipate them. Because, well, the point really is anticipating. That's why we have scientists chiming into the discussion. And thus, I think there is a need to optimize negative emissions portfolios, and in fact, within the context of general decarbonization portfolios. And understanding future carbon markets and business models that will form the scaffolding for the commercialization of these technologies. Okay, thanks very much. I'll be happy to proceed with my colleagues and co-panel members to the discussion.
Thank you very much. So I'll just be spotlighting our panel members. And if you have any questions, please feel free to type it down in the chat box. So I think, yeah, this is a very pressing issue for everyone, and it's really a concern for everyone. Maybe I'd like to get your insights on how the okay, Al has something before I go on. Okay, Al, yes, please feel free to unmute yourself and ask a question. Thank you.
Thank you. Okay, I'm saving you for because there's three burning questions essentially for me that just happened actually in the Philippines. You were aware that there was a Christmas storm that plowed through Siargao all the way down to Palawan, and that has caused a damage that's almost, not a lot of people know it, it's almost equivalent to Haiyan or Yolanda. And one question is for Joey. Joey, this is a December 25 event. And I was wondering, when you said Haiyan had the highest temperature in 2014 when it happened, I was wondering what was the temperature of the Pacific on the eastern side when this Odette was born. And if that would have been predicted, it could serve as a warning for us, saying that we're not out of the hole yet, even though it's December. The ocean's still warming, and you might still expect another Odette this coming 2 years or something to that event. So that's one. And for Juice, definitely the business impact of such an event is not properly, for lack of a better word, assessed in my book, because it only does the stock impact, as you mentioned, not the business interruption part. And clearly, for me, Raymond, I'm looking forward to discussing what portfolio we can come up in the Philippines that's viable for net. But I think I can ask that those are my three questions for each and one of you. So I was listening just to let you know. Thank you. And I look forward to your answers. Thank you.
Yeah, I guess to answer the question about temperature in the Pacific Ocean, that's not routinely available, and you need to process a lot of data to do it. And I think it should be the responsibility of the Philippine Space Agency to be doing this. But right now they're underfunded, and I wish the government would provide ample money for them to routinely analyze satellite data, so we can map what's going on in Western Pacific Ocean and be able to know in advance the typhoons that are potentially very dangerous to the country. So since I'm retired, I cannot really do much about it at the moment, but I can guide people working at the Philippine Space Agency to do it. And we can analyze the data to look at the correlations.
Okay. Thank you, Joey. Definitely, Joel Marciano and Jay Perez will be very happy if you offer your assistance to them. I know you published the paper together for Haiyan with Jay. So I think maybe Odette might be another one that if you can predict it even months ahead so that people don't relax just because it's Christmas season. Thank you.
This is Juice. I'm very much impressed. I've always been impressed by Al. But I would just like to give you a shout out for remembering the stock and flow damages. So you're correct that the immense damage from Haiyan and the most recent typhoon that just made a landfall over the Christmas season. It's so immense, the human capital and also the infrastructure damage. In my presentation, it's just one of the case studies that that business interruption is going to account approximately for the 70% of the total economic losses. So the human capital unfortunately cannot be recovered. Damage the infrastructure systems, you can restore them. But for business interruption, in our study, we're able to prove that some mitigation strategies like relocation of damaged facilities, inventory, and also over time shifting workload, the time schedule for workers can actually have an immense impact on saving the losses for the business interruption part. So for the capital, for the stock flow, it's irrecoverable. But the good news, if there's like a silver lining here, it's the business interruption that we can mitigate and ultimately save us a lot more money and give us some lessons in the future to do more planning for future disasters. That's all.
Okay, Raymond?
Thank you, Al. First of all, I want to say that the sexiest negative emissions technologies, as far as media is concerned now, internationally, are either direct air capture, that photograph I showed, or bioenergy with CCS. The problem is both of these require geological storage. I mean, it's one thing to take the CO2 out of the atmosphere. What do you do with this once you've captured it? And a bit more than a decade ago, I was involved in an ADB assessment of the potential in the Philippines for storing CO2. Long story short, the seismicity of the Philippines is an obstacle. The reason we don't have natural gas and oil reserves through most of the Philippines, except for the western portion, which is actually part of the Asian mainland geologically, is because the reservoirs don't last long enough to securely hold fossil fuel reserves. And that argument likewise goes for CO2 that we might capture. So that's disqualified as far as the Philippines is concerned. And actually, I want to say a couple of things as well. The Philippines, unfortunately, is trending towards increased coal power generation. I think that's going to be problematic as we see electric vehicles coming into the picture and internal combustion engine vehicles being phased out over the next generation. So that's one part of the problem. In terms of the lowest tech technology is simply afforestation and reforestation. The problem is we have a long way to go because we actually have the deforestation problem, and we're not just going to have to arrest the deforestation, we're going to have to reverse that and create new forest area while squeezing in 110 million people within the same set of islands. So what are some of the low-hanging fruits that I think a country with plenty of agriculture might need to explore? One is something which I actually learned from a geologist colleague at the University of the Philippines, which is that weathering of minerals can be accelerated, and some of these minerals actually very slowly react with CO2 in the atmosphere. you can engineer systems so that you can make that much faster than a geological pace. That's called enhanced weathering, and that simply means you take the selected minerals, grind that up into a fine powder like flour or cornstarch, and then apply that on either marginal or agricultural land. Now, if you do it with agriculture, there are some bonuses like typically improvement of soil quality and improved productivity. The second low-tech approach, which I think I've spoken about before, is biochar, which is a bit like it's a bit like compost, but you would use carbonized biomass, which is very stable. It decays very slowly. And again, you grind that up into a fine powder and then you use it as you would compost on agricultural land. And it does two things. It improves your soil and it locks up the carbon in the soil. So I think those sorts of low technology solutions need to be explored. People need to understand that those work not just from an agricultural standpoint, but from the sequestration standpoint.
Thank you, Raymond. Definitely, that's both considered. One only aspect on forestation is definitely the consideration for marine forestation, which is the mangrove. As you know, we did award a Ramon Magsaysay awardee in Zamboanga, Sibugay this year, and his rehabilitation of 30 years or 40 years on mangrove. I would want to see if there's indeed a carbon potential capture on such a effort, but I'm not gonna belabor the issue. I'll let other people to ask the questions as well. Thank you.
Okay, I think Giselle has a question. Giselle?
Thank you. Thank you, Kay and Raymond. I'm happy to hear again your talk on carbon drawdown. And well, yeah, I was just drafting a paper for Star Science on chemical science as a way of life in the VUCA world. And the VUCA world is actually, dominated partly by climate change considerations. So thank you for your talk. Now I tend to try to review the chemistry, the basic chemistry, although inorg is not my specialization, but maybe it's just time for you to enlighten us on the equilibria that exists among these entities, the carbon entities, which would be carbon dioxide, carbonic acid, and calcium carbonate, because you're proposing that carbon dioxide be locked into calcium carbonate in strategic places. But from the marine perspective, well, where I am very interested in, I would be interested to know how calcium carbonate deposits might contribute to further ocean acidification. And we know that it is a vicious cycle. It's a self-perpetuating cycle, that if you have high acidity in the ocean, and then you have a calcium carbonate that comes in through siltation, sedimentation, and leaching, and erosion to the oceans, then in fact that acidic ocean might get the calcium carbonate to convert to more carbonic acid and carbon dioxide in the oceans, which would be very detrimental to marine life. On the other hand, we know very well that there are shellfish and other types of marine organisms that need the calcium carbonate for their shells, for parts of their body. So I'd like Raymond to expound a bit more on the basics of this equilibria, among the carbon entities. Thank you.
Yeah, thank you for that, Giselle. First of all, congratulations on reviving Star Science. I actually, first thing is, because we have such a limited time, what I'll do is I'll share a paper that I wrote with Kay about a year ago, which was accepted about a year ago. And maybe we can work on turning that into a Star Science article within the next month or so.
Fantastic.
All right, but a very quick chemistry lesson on enhanced weathering. There are two pathways here. Basically, you have the carbon dioxide and moisture in the environment, and you'd have, for example, typically silicates that exist in rocks and minerals. Now, one pathway is enhanced weathering, and that basically what happens chemically is carbon switches places with the silicon and the silicates, and what you have is a silica residue where the reaction takes place. But instead of carbonate, you actually get dissolved bicarbonate ions in the runoff water. Now take note, this all occurs at the interface where the water meets the mineral. And it's a very dilute aqueous solution. And the runoff basically carries the dissolved bicarbonates into rivers and ultimately, of course, into the sea. But the chemistry is actually favorable in the opposite direction, because when you have dissolved bicarbonate, that's very slightly alkaline and will actually serve to offset some of the acidification problems that are occurring. Now, that's the general chemistry behind it. Whether you'll have localized excess alkalinity, that still remains to be seen, but the work of Phil Renforth in Heriot-Watt University certainly speaks about such issues. Now, in terms of, there's an alternative pathway which is known as carbonation, where instead of having dissolved bicarbonates as the ultimate sink for the carbon, it's actually solid carbonates. This has been observed in the field, for example, in the UK and other places where there are steel works and iron works. The slag stockpiles, they actually just stockpile the waste material from steel and iron production. There is published documentation of the accumulation of carbonate residues as a result of decades of carbonation reactions. But eventually, once you have the encrustation of the carbonates, then it reduces the surface area contact and it slows down the reaction thereafter. So the problem there is, how do you have enough surface area so that the reactions continue at the pace that you need to continue to sequester the carbon? All right, I'll stop right there. And I think,
Okay, yeah,
as I promised, I'll write up a Star Science paper on this.
Okay, thank you. You actually have a related question coming from Biswajit. So it's in the comments, it's in the chat box. So Biswajit is asking, how do we collect data for carbon dioxide emissions for each country year-wise? And why do researchers only bother about carbon dioxide and not other emissions like carbon monoxide or other greenhouse gas emissions, perhaps? Is it possible to make a carbon capture system to reduce those emissions, maybe apart from carbon dioxide? What is your point of view in this direction?
Can I answer
Sorry.
that?
Oh, sorry.
Yes.
Yeah, there are actually satellite sensors now that can measure carbon emission from different regions of the world. And they call it XCO2. It integrates the emission and the amount of carbon within a vertical column. So you can see the areas in the world where emissions from carbon dioxide are strongest. And you can see emissions from Japan, from China, from Europe, from the US. So eventually we'll be able to monitor where all these emissions are emitted, where all these carbon dioxides are being emitted. And we can figure out how to resolve the problem by confronting countries who have excess emissions.
Thank you, Joey. Any thoughts on that, Raymond or Just? Any additional comments?
Sorry, Just, you were about to speak. Go ahead.
No, I was shaking my head.
One of the things I want to mention is, speaking of other greenhouse gases, methane is the second largest contributor. And one of the positive results of COP26 was better focus on methane management. For example, I personally have made it a point to eat much less meat, partly for health purposes and partly as my tiny contribution to decarbonization because of methane emissions in the agricultural supply chains. So that is low-hanging fruit. Every little bit of decarbonization helps. Thank you for that.
Well, in terms of methane, actually, the warming in the Arctic could cause a thawing of the permafrost. And so actually in the permafrost areas where about 80 to 90% of methane is still stored. So that can be a big problem, if we continue getting the Arctic region to warm up.
Okay, thank you for that. Maybe I have a question for, I don't know, maybe Joey will be the best one to answer this one. But seeing the increase in temperature because of the increase in carbon dioxide emissions, if we do manage to reduce, for example, like how fast does the environment react? Like, can we really arrest the increase in temperature if we manage to reduce carbon dioxide emissions in the next 10, 15, 20 years?
Well, actually, in the IPCC 2014, if we keep the carbon dioxide stabilized and not get it to increase any further than 421 parts per million, that was the level when we were doing the IPCC 2014, then the temperature will stabilize as well. So we're talking about increase in temperature of 0.5 from what it is now. And, the uncertainty in the estimates is probably within that much. But if we can keep the temperature within the present and 1.5, because we are doing our thing in terms of limiting our emission and keeping the percentage carbon dioxide not to increase any further than what it is now, then we'll be doing a good job.
Okay, thank you. Okay, we have a few comments from Hill. So the first one is on the issue of deforestation and afforestation. It seems to be a viable option. It is a low-lying fruit option to help address carbon emission and sequestration. And then globally, limited financing has become available through the Green Climate Fund and the Global Environmental Facility, where carbon emission control and management are at the center of their mandates. And then finally, he says that it would be interesting to look at the cost of capturing carbon through technology, such as geoengineering, and the cost of sequestering them through biomass. So perhaps you have any comments on those things. Yeah.
Thanks for the comment, Hill. Kay, can I comment on this?
Yes, please. I
certainly agree with you that the low-tech option of reforestation and afforestation should be a major part of any portfolio. I think the problem in the Philippines and many parts of the developing world is that before we can even get to that stage, as I said, we need to arrest the deforestation which is already occurring, and stopping it is not going to be enough. From a carbon balance standpoint, as Freeman Dyson pointed out 45 years ago, what we need is not zero deforestation. What we need is creation of new forest land. And that is the challenge which we're facing. I think there are some opportunities. And in terms of research, I'm a believer in having a portfolio or a mix. And I think within the global research community, you need to have the oddball speculative ideas at one extreme, and at the other extreme, you need the technologies which are on the verge of making it into commercialization. So we need a mix of all that. And one thing that would like to point out a fellow by the name of Gall and his colleagues published a paper in Nature Geoscience last year. And this is really one of those highly speculative ideas. They said they did some calculations on taking aircraft and dusting remote ecosystems with pulverized minerals. You know, when you have forest fires, for example, in California or in Australia, normally you have these aircraft which would dust fire retardants on the flames. They suggested that you could do the same, but you'd take pulverized alkaline minerals and dust remote ecosystems, and that would do a couple of things. Through weathering, you'd have the direct carbon sequestration through geochemical reactions, on top of which that if you were to do that properly, for example, perhaps with the aid of satellite imagery, picking the right spots where you do the dusting, you'd stimulate biomass growth further on top of the background levels, and thus have secondary capture of carbon dioxide. Again, that's very speculative, but those are some of the solutions that we need to be at least thinking about. Whether they make it into real decarbonization techniques after a decade or so, that remains to be seen. But in terms of research needs, you need wild ideas like that as well.
I would like to add to that. Actually, there's a national greening program in the Philippines, and the plan was to spend billions of pesos. Actually, the idea was to allocate millions of hectares of land to be planted, and they prepared, I think, 1 billion seedlings to be planted in this area. And after 4 years, they reported so much success that they indicated that we should have this to be continued for another 4 years. So it's still ongoing. However, when we look at the areas where they think they were very successful using high resolution satellite data, we found out that in these areas, the net increase in forestry is not actually positive, it's almost level, because in addition to having reforestation in these areas, there's also deforestation, which is even sometimes stronger than the reforestation. So what's needed is better monitoring on this, and a stricter enforcement of rules in terms of deforestation, because we have noted that even in areas, which are declared as supposedly untouched areas like national park, there's still deforestation going on. Now, in terms of geoengineering, actually that has been rejected by the scientific community for a while, until 2 Nobel Prize winners started endorsing it. So they became serious at looking into that. But the options that were offered were to introduce a lot of aerosols in the atmosphere, for example. And nobody knows the consequence of having a lot of aerosols in the atmosphere. You can have a beautiful sunset, but what happens to the rest of the world, what would those aerosols do to the climate? And also, you mentioned actually, Raymond, about the fertilization of the ocean. And that means putting a lot of iron in the ocean, because iron is actually the key to enhancing the productivity of algae in the ocean. But that would be a lot of iron. I don't know where they would get enough iron to really maintain that. And in the case with aerosols as well, it's very expensive to keep the aerosol maintained in the atmosphere, so it continues to cool the earth, while at the same time we continue to emit carbon dioxide. So it's a difficult problem. And I think your idea about forestry and biochar is a good thing if we can make it, globally, so that everybody does the same thing.
Thank you, Joey. I think Hale would like to add on to his comments.
Yes, thank you, Kay. Just a few comments. And first of all, I think I agree with what Raymond indicated earlier, that we do need a portfolio or a suite of approaches and solutions to be able to address this, perhaps minimize, or do what we can. And I'm glad that Joey somehow mentioned about the Philippines, because I would really like to take the conversation to the Philippines, just not looking at the big pictures, but looking at what can actually be done, what has been done in the Philippines, because as we all know, and our history has shown, that we are perhaps the most vulnerable of many countries as far as the negative impacts of climate change, flooding, earthquakes, and so on. On the issue of deforestation, I think, I think we don't need to wait to arrest deforestation first before we actually consider doing something in the afforestation side. I think this can be done in parallel. In the Philippines, as noted by also Joey, the major problem of deforestation is essentially conversion of forest land into agriculture, just because many of our countrymen just don't have land to till. So this again should be addressed in a more systemic and systematic thinking, and not just in a piecemeal approach. I think the Philippines is doing some of this through our DANR. The NGP is one of those programs, along with others. There are also some, not just on the biophysical side, but even instruments from the economic side, so that you incentivize people that are actually doing reforestation. And you also incentivize countries or people or communities that are avoiding deforestation. So that, I think, should be a part of the strategy to be able to address this. And lately, we are also now beginning to engage the private sector as well, because I think this is also a problem. And we sense the interest also of the private sector to be involved in some of the issues that we mentioned here. So some of that is also now being put in place. I've been involved in some GEF and GCF project along with FAO and DANR on some of these things. Now, these are maybe not the scale that thinking here, but I think we need to start small, and as we develop more knowledge and experience from this, I think we can, at least in the Philippines, do our share in addressing this. But more importantly, I think not just mitigation, the global problem, but mitigating it so that the country itself can adapt to the negative impacts, because really, as shown by the graph of Joey also, we are not a major emitter compared to China and the US. And so I think we need to pay attention to what really would serve the country better, also in terms, even as we think about what can be done about this. Thank you for the opportunity to comment.
Thank you, Hill. And maybe I'd like to ask Juice as a follow-up, because you mentioned a while ago about the benefit cost ratio analysis that can actually be done on certain technologies. Can this be implemented also, for example, on the negative emission technologies being mentioned by Raymond? And can these be done on a regional scale? And what kind of maybe information would be needed to perform such kinds of analysis?
Yeah, so what happens is that when you implement those solutions to reduce the vulnerability of regions against climate change effects like hurricanes, earthquakes, liquefaction, and so on, droughts, heat waves, is that you'll also be able to avert potential losses. So you'll be able to save on potential damage to buildings, bridges, infrastructure, and also you'll be able to save on business interruption losses, which I've emphasized to be as almost more than significant than the losses from the stock losses. So yes, if we were to include for example, one of the things that we did was strengthening the building codes for the United States. For example, the two states with the most stringent building codes happen to be Florida and Virginia. So by strengthening those building codes, among other potential solutions to adapt to climate change, will be able to provide more compelling reasons for mitigation solutions, thus potentially increasing the benefit to cost ratio, which I mentioned to be 6:1 for the United States on average, and for the Portland study, it's a 12:1 ratio.
Okay, thank you. Before I go on to the question of Jeremy, I saw a related question regarding your Portland study. So it comes from Alan of TIP. So what is the time frame of your research for the Portland airport for the potential for significant cumulative effects from sea level rise and earthquake events?
Yeah, that's a very good question. And if I can just show a slide, which I didn't include in my presentation, which will be better to show to effectively answer the question. So we actually considered 5 scenarios. And most of you are already familiar with these magnitudes at the bottom. For 8.7 magnitude with a return period of 72 years. The second one is magnitude 9.12, return period of 225 years. And I don't want you to get bored with the details. We also considered like 2,000-year return period events. But as what the United States Army Corps of Engineers said, like hurricanes with 100 return period, 100-year return periods, actually, it's a misnomer. It's actually easily misinterpreted when you say 100-year return period, that on average, the next Haiyan will come back after 100 years. It's actually going to confuse people and probably degrade the potential to create more effective policy. So we'll just leave it at that. So although these are based off on return periods, I hope everyone is not making the easy mistake that 72 years, for example, here means that this magnitude of an earthquake has an inter-arrival period of 72 years, which is not even like the lifetime, almost like the lifetime of one person. So to cut the story short, even if we're talking about 100-year return periods, it could easily arrive like maybe a year or 5 years from now. So that's all.
Okay, there's actually a related question. I'm not sure if you were able to read it, but what are the appropriate considerations of increased liquefaction to sea level rise to safeguard investors, regulators, and the public, especially on developing commercially and aesthetically attractive coastal expansion that account for hazards associated with climate change?
So for this question, I may need help, what do they call it? Like a lifeline. But all I can tell you is that the one most obvious answer to this question is avoid the coastlines. And one of the things that I also said in the earlier answer is enforcing more stringent building codes. And aside from that, I'm not a geotechnical engineer. So maybe I need some help answering this excellent question.
Yeah, perhaps Raymond or Joey can comment.
Let me try something here. I think one of the psychological and mental challenges of dealing with climate change and being prepared for that is humans seem to be programmed to assume a steady state. Our agriculture, for example, is predicated on having seasons which recur year in, year out. When you put up a factory or a building which has a lifespan of, say, 4 or 5 decades, you expect more or less a recurring pattern of weather and climate during the lifetime of your investment. And this is where climate change is very difficult to deal with, because the fundamental lesson is that the world is going to be different 3-4 decades from now when you make the investment decisions. So number one, I think, is just that recognition that you need to build a scenario for what the environment of your investment will be like by the time it approaches maturity or end of life. So if you're putting up, for example, a power plant which needs to be by the coastline, is that coastline going to move over the next 1, 2, 3 decades as your power plant operates? Then you're gonna have to factor that into picking locations, picking out how the buildings are put up, and so on and so forth. Okay, thank you for that.
Okay, so thank you. Joey, do you have anything to add?
About liquefaction, that normally occurs when you have reclamation in certain areas and you have earthquake, for example. Are these the kind of example you were looking at, Gus, or?
For Portland, because of the unique geography of Portland, the trigger for the liquefaction was earthquake.
Okay, so that might not even be related to climate change.
So thank you. We have a couple of questions left. Okay, one comes from Jeremy and it's addressed to Dr. Tan. So how is double counting avoided in carbon markets? And how can we ensure that the carbon absorbed by one technology or net company is not sold twice in the marketplace? Do you think that blockchain technology can help solve this problem?
Great question. Actually, this is a point that is addressed in one of the perspective papers that I showed earlier. You can get that on Science Direct. Essentially, it would be like trading any other commodity. Carbon credits will be traded as an intangible commodity. And part of what I see emerging in the future, you can come back in 10 or 20 years to figure out if what I'm going to say will come true. But I think there will be firms whose business model will revolve around verifying the credits that are sold between third-party firms. So these are like, these will be like financial firms which do audits and such. So I think that will be part of the business environment in the future. Thanks.
Okay, thank you. And then
Can I add something to that?
Sure, Hill.
Yes, because at least in the forestry side, there is already a market model that's developed exactly what Raymond is saying, and that is, if you're going to reduce your emission by a certain amount by not deforesting, then you need to be paid for that service. And so there is a money, some funds set aside actually for the purpose of incentivizing countries like the Philippines, Indonesia, or South America, so that and the system is already in place, so that they have to be verified. They have to be the accounting, the assessment have to be technically sound. Somebody has to come and look at it and say, yes, this is the carbon credits that you are allowed, you can be given carbon credit for. And so the verification process has to be also stringent, including other issues like political and institutional and all that. And so I think, again, this is part of the portfolio of approaches that we can do. But I'd like to change that topic a little bit and come back to the Philippines, because what we are proposing, and this is harnessing the interest of the private sector to be engaged, is not to look right away at the economic side, the market side, although, maybe eventually it will evolve to a market system, but make it through the corporate social responsibility side. so that a private sector who might be interested to work with a community in upland, then instead of the upland community continuing to deforest, to degrade the area, they can restore it, and then for whatever carbon benefit can accrue from that effort, then the company can then use it as its CSR. In other words, it can claim the credit that as a result of what we have been doing with the community, we sequestered 10 million of metric tons of carbon or something like that. So I think the market economy, I think, is still a long ways to go, but I think we need to look at it both from a regulatory standpoint as well as from the economic standpoint. Because looking only at the economic standpoint, I think it won't fly in the near future. But if we have a mandatory carbon offset system in place, then I think along with the economic incentive later on is probably a better way to go.
Thanks for that, Hill. Oh, and then yeah, we just have another question from Giselle. If you have any comments about how intact is our ozone layer right now? Does anyone have?
Ozone layer in the south or everywhere?
Both, I guess.
Everywhere?
It has stabilized in the south. It's still a little low. I mean, the hole is still there, but it hasn't continued to decline. I mean, to increase in size.
Okay, so thank you. So I guess that's all for the questions today, but I'd like to get the final words from our speakers. Some parting words for our audience, perhaps some of your ideas on how we can actually achieve the targets so that we can arrest climate change. Joey?
Yeah, actually, I initially had 15 slides. And then when I realized I only have 8 minutes, I actually cut it short, and I was not able to show some of the relevant stuff in my talk. The thing there is the IPCC 2014 and the IPCC 2021, the conclusions are basically the same, but there are improvements in the modeling that are used in the IPCC 21. So we already indicated that much of the extreme events that we are experiencing attributable to human activities in 2014, but in 2021, then they reinforce this, and they have much higher confidence that it's indeed being affected by human activities. I mean, the extreme events. So the other thing is the fact that there is this 1.5 degree limit. So at the beginning, I was quoting the American writer, Henry Thoreau, just got over a passage where he said, "What is the use of a house if you haven't got a tolerable planet to put it on?" And I think that was really a intuitive comment. The fact that actually right now we want a tolerable planet, but we don't really know what it is. I think 1.5 is not really that well studied, an increase of 1.5. Right now, a lot of people are complaining already about the fires in California, all the flooding that's going on in the Midwest, in other places of the world. So the thing there is 1.5 really the ideal temperature, or what Raymond is saying, for example, as trying to capture carbon so that we'll get into much lower carbon dioxide percentage in the atmosphere in order to reduce the current temperature further would be more ideal or not. So that's really something that we have to think about. What is the temperature that we as human beings are most comfortable with? I don't know whether we really have the exact answer for that.
Thank you, Joey. Juice?
I'd like to re-emphasize that disaster risk management is comprised of managing both the stock and flow losses. And what I hopefully have successfully shared with the crowd here is that interdependency is ubiquitous in today's world. That if I can just quickly use the term or the phrase butterfly effect, that even the minuscule changes in one region maybe have some long-lasting and adverse impacts on other surrounding regions. So we now live in an interdependent world, which is good, but it also has some setbacks in terms of the coupled ripple effects. Disasters can debilitate the infrastructure systems and also the economic transactions, not just with regions with the independent regions, but also we have to look at it holistically. So there's I'm becoming nostalgic now. I studied also at the University of Virginia. So one of the things that my advisor, Professor Jacob Hames, told us is the acronym NIMBY, which is not in my backyard. So it's also an acronym and also a concept that's also relevant to the topic of climate change. So I don't want to sound like idealistic, but it really is a matter of helping everyone, like all nations. All the leaders should be invested into combating the problems, the depressing problems associated with climate change. And if you are asking me for a recommendation for something to watch, just if you have a Netflix subscription, just look for the documentaries by Sir David Attenborough, which I truly enjoyed watching. Yep. It's kind of depressing, but at least if everyone here in this world will watch that movie, I truly believe that it can have like a positive domino effect or butterfly effect, waking up everybody that that climate change is really a serious issue. Thank you.
Thank you, Juice. And then finally, Raymond.
Thank you. My parting words are for the young researchers and graduate students in the audience. And think of this either as a pop quiz or as a thought experiment. Which is better for climate change mitigation? Taking out 1 ton of carbon dioxide in your home country, whether that's the US or the Philippines, or doing the same thing in China or in India? The short answer is ultimately it doesn't matter, because that all goes into the atmosphere. There are no national boundaries that keep CO2 emissions from the Philippines hovering just above the Philippines. And ultimately what that means is if you're doing serious climate change mitigation research, you need to adopt an export mindset. you should target a global audience, because if your ideas reach people in other countries and they eventually scale that up and mitigate emissions in different parts of the world, that creates a lot more good for humanity than just keeping it within imaginary nationalistic boundaries. So do research for the good of humanity, because after all, your home country is part of humanity. Thank you.
Thank you for that. And I hope that leaves everyone with something to think about in the next coming weeks. But before we end, so let me just share my screen. So I've already sent you the link for our evaluation form. So you can scan it here. So please send your comments in the eval form at bit.ly/eval_Jan21. And then I'd like to plug the next webinar, which will be next week. Also at the same schedule, 8 o'clock in the morning, Friday, we'll have Dr. Leon Clark to discuss the implications of city, state, and business climate leadership in the United States. So if you're interested, please register at bit.ly/PAASE_Jan28. And then for those of you who'd like to see all our previous webinars, you can find us on YouTube at PAASE Webinars. And to get updated on our other events, we have paase.org for our website. And with that, I'd like to close this forum. Thank you very much, everyone. Happy Friday, happy weekend, and hope to see you in the next webinar. Thank you, guys.
Thank
Thank
you.
Thank you.
Thanks,
Thank you, everyone.
Thank you.
Good job, guys. Thank you.
Great job.